Boston, would you please go to the slide with the model and with image of the model?
This one?
Yep, and explain a little bit more why some authors call it two-dimensional material, and two-dimensional in which directions? Like, what are the axes here?
Yep.
And why did you explore momentum dispersion in X and Y and not in Z? So please tell more about it.
Yeah. So Bismuth Telluride, in the axis that I have shown here, the Z-axis is up and down. That is the That's the axis where I only had the one point in the K-point mesh, and the plane is the XY plane, where it's 2D, and it's considered 2D material because of van der Waals separations between each layer of bismuth telluride, kind of similar to graphene, if I'm not mistaken. My understanding of that is still relatively limited. I'm doing my best to learn, but that is, to the best of my knowledge, what's happening there. And did that answer your question fully, or was there anything else that I skipped?
Yeah, it answered first part, but the second one, can you please show your momentum dispersion?
Yep.
Which is it is quite an achievement to. So it's let me make a comment. Unlike standard approach in community where one explores momentum dispersion along high symmetry points, Boston is doing full scan of all values of momentum in X and Y direction. And it looks like he's showing top of the valence and bottom of the conduction bands. But there is a scan along X and Y. Why you are not showing scan along Z? What would you expect?
Yeah, I have, I think, a slide for that. Let me skip way forward in my, I think I had a slide for it. Oh, no, hold on.
You can tell just by words.
Yeah, okay. So again, my understanding of it isn't that strong, but it shouldn't really change too much between or in the Z direction of the material.
Oh, you're telling me it will be flat.
Yes. And again, my understanding as to why that would be is relatively limited at the moment. That's something I still need to look into.
Let me provoke you. Would you agree that in Z direction it will be more insulating and X and Y it will be more conducting?
Yes. Yeah.
Okay. More questions from...
May I?
Yeah, please.
Okay. So Boston, the first one is more like comment.
Mm-hmm.
There are two important effects, in this material. The first is spin orbit interaction. Both bismuth and telluride are heavy elements, so that's where bismuth telluride, has very strong orbit interaction. So if you include that effect, the electronic structure and the optical properties may be significantly different. That's the first thing. The second thing, you also mentioned that there may be van der Waals interaction, between the layers. So if you include that, you also see changes in the electronic structure, and I don't know how much it's going to change. Okay, that's my comment. Now the question is, I saw that you did some MD simulation.
Mm-hmm.
What is the purpose of the simulation? Because I thought that you are doing static calculations.
Yep. So I want to do a lot of different things with the material. I was limited by time to get some of these things done, but I wanted to study the material at different temperatures as well. I only got around to doing a 300 Kelvin one. I want to the static properties were the ones that I was most interested in, which is why I stuck to those more than the molecular dynamics run. But in the future, I want to do more molecular dynamics run and see how those affect the system at all, including other properties that I haven't had time to talk about or haven't even had time to go into research yet. But I mostly just included it because it was done and it was relatively interesting. But again, the static properties, as you pointed out, were the ones that we're more focused on and was kind of the primary area of the research that I've done so far.
Yeah.
Does that answer your question? Hopefully.
Yeah. Thank you.
And no more questions. Last question on the account of exam for computational chemistry. What is self-consistency in Artifoco in DFT? And if you have some illustrations you can show.
Yeah. So this is kind of a general flow chart for the algorithm or the self-consistent process that VASP and other, I'm sure other DFT programs use. But basically, you start with some initial conditions, and then it starts running through these equations and updating the total energies, and it keeps looping through these until the total energy between individual steps is less than some energy cutoff value that you set. And that should mean that you're at the minimum, the ground state energy, which is what you're generally trying to get to in these calculations. And so that's, you're self-consistent with itself. It just loops through and compares new values that it's calculated to the old values, and then keeps trying to get to the lowest potential that it can, which is the low, and it calculates that through the density functionals. So to the best.
No, that's great. That's great. Yeah, thank you. If there are no more questions, please join me in thanking Boston once again. And